Hello, ladies and gentlemen. It's Matthew Faro here again, and welcome back to my space. It's that time of the year where students, especially calculus students, prepare to take tests and examinations. And out of my busy schedule, I stumbled upon this nice looking packet, a mock test to help students prepare for their forthcoming examination. And they were too tempting to look away from. So I decided to make some videos out of this. For this particular video, I'm going to extract the integration questions out of this set of problems. And probably in the subsequent videos, we'll look at the other parts of the questions. So without wasting too much of time, let's get right into it. So the first integration question here is number 7, which requires that we integrate the square root of 7 plus 2x over 7 minus 2x with respect to x. So one of the problems of integration is knowing where to even begin. Unlike differentiation, when you see a question in differentiation, you know exactly what to do. But for integration, sometimes if you've not seen a question before, it can be a little bit tricky to know what to do. So in this particular case, what I will try to do here is to see if conjugation or rationalization will help. Then let's get started. So in this case, we will rationalize the denominator. So 7 plus 2x over 7 minus 2x times 7 plus 2x over 7 plus 2x. We are multiplying by the conjugate of the denominator, so with respect to x. And the numerator becomes, so this is square root of 7 plus 2x all squared over, then we use the difference of 2 squared with the denominator here. That gives us 7 squared minus 2x all squared. With respect to x, and this gives us the integral of, so the numerator just becomes 7 plus 2x, and the denominator becomes the square root of 49 minus 4x squared with respect to x. And these we can split into 7 over square root of 49 minus 4x squared dx plus the integral of 2x over square root of 49 minus 4x squared with respect to x. Now, there are different ways we could approach this, but one thing that has popped up to me right now, seeing these numbers, this is looking like a trig substitution. And since we can see what is happening by drawing a triangle, we can go this direction. So the fact that I have square root of 49 minus 4x squared, that is speaking to me as if we have an hypotenuse of 7 and an opposite of 2x, such that using the Pythagoras theorem, hypotenuse square equals to opposite square plus the adjacent square of a right angle triangle, then the adjacent will be the square root of the hypotenuse squared minus the opposite square, because I'm seeing square root of something minus 4x squared. So the adjacent here is the square root of hypotenuse, which is 7 squared, that is 49 minus 4x squared. So this would be an appropriate substitution to do. And what is that substitution? Using this triangle, we can see that sine theta is equal to 2x over 7. We also see that cos theta is equals to square root of 49 minus 4x squared over 7, and tan theta is equal to 2x over the square root of 49 minus 4x squared. So that means the right substitution for us to use, right, from this first statement is to say that x is equal to 7 over 2 sine theta, and also that gives us that the x is equal to 7 over 2 cos theta. We also know from here that theta equals to arc sine 2x over 7. With this, we can rewrite our integrand to be equal to the integration of, so 7 over square root of 49 minus x squared is just the reciprocal of this cos theta. So that will be 1 over cos theta times, so from here we can see that the x is equal to 7 over 2 cos theta d theta. So this is times 7 over 2 cos theta d theta, then plus the integral of 2x over square root of 49 minus 4x squared. That is exactly what we have written here as tan theta. So that is tan theta, then dx here is equal to, again, 7 over 2 cos theta d theta. Beautiful. Now we can see that 7 over 2 is a common constant in both cases. So we can pull that 7 over 2 out. So we have 7 over 2 times, also cosine of theta cancels cosine of theta. So we are left with just the integral of the theta on the first side. And on the other side, we are going to be left with tan theta times cos theta. But of course, tan theta times cos theta is equals to sine theta. Since tan theta is equal to sine theta over cos theta, so this is tan theta. So when we multiply that by cosine of theta, so we end up with sine theta. So sweet. That makes this expression even simpler. This is sine theta d theta. Now we are just left with simple integration. So the integral of the theta is just theta, and the integral of sine theta is negative cosine of theta plus c. We'll be done if not for the fact that the question was given to us in terms of x, so we need to bring back the x. We need to go back into the x world. And remember that theta is equal to sine inverse of 2x over 7. So this becomes 7 over 2 times sine inverse of 7 of 2x over 7, then minus cos theta. We've seen cos theta here to be the square root of 49 minus 4x squared over 7 plus c. So this is basically the answer, but if we like, we can distribute the 7 over 2. So we have 7 over 2 sine inverse of 2x over 7 minus 7 over 2 times the square root of 49 minus 4x squared over 7 plus c. Then this is equal to 7 over 2 sine inverse of 2x over 7. Then the 7's here cancel out, and we'll be left with minus 1 over 2 square root of 49 minus 4x squared plus c, which is a beautiful answer. That takes care of the first one. Then the second integration question, so we're done with this second integration question, and the list is this guy here. So let's copy and let's paste it here. No, that's not what we want. We want to bring this guy, copy, here, paste, finally. Good. So in this second question, we are looking at the integral of natural log of sine x over sine squared x. This is a fraction, and it doesn't look like a normal u substitution will work. So because that is one of the first things to think of when you come across a quotient. So what can we make as u to make things simple here? If we say u is equals to sine x, it doesn't help us because we end up with natural log of u over u squared, and there will be a cos x showing up somewhere that will not get cancelled out. Okay, that does not work. So can we make u equals to natural log of sine x? I don't think that will work as well because we eventually get cot x. Oh, okay. So what works eventually? So if you look at this carefully, you see that we can rewrite this as the integral of natural log of sine x times 1 over sine squared x. And that's basically the same thing as natural log of sine x times cosec squared x dx, since 1 over sine x is cosec squared x. So why do we have to see it this way? This is because this is now a product of two things where we know the derivative of one of them and we know the integral of the other one. So in integration, when you have something like that, the best thing to do is to go with integration by parts. So when you have the product of two things such that it is easy to differentiate one of them and it is easy to integrate the other one, it's most likely going to end up being an integration by parts question. And if it is exactly f prime of x times f of x, that one would actually be u substitution. But in this case, it is just the antiderivative of a different function and a derivative of a different function that we have here. So, and you remember that the formula for integration by parts, IBP, says that if the integral of u dv is equals to uv minus the integral of v du. So the next thing is for us to identify what will be our u. And in most cases, if you don't remember the acronym for the preferred hierarchy, just remember that what you know its differentiation is what is likely going to be your u, and what you can easily integrate is what should be your dv. So it is always very easy to differentiate natural log functions because the differentiation of natural log of f of x is just f prime of x over f of x. That is, you differentiate what is inside the parentheses, which gives you f prime of x, and divide it by the f of x. So it means we can do u equals to natural log of sine x and dv is equal to cosec squared x dx. Beautiful. So from what we just said, the u will be the differentiation of sine x, which is cos x over sine x itself dx. That's basically just cot x dx. So that's our du. Then what about our v? So one simple trick that I usually use is the fact that I know that the derivative of tan x is sec squared x. So, and since cot x is the complementary function of tan x, its derivative will be the negative of the complementary of whatever we got with tan x. So that would be negative of cosec squared x. So it works for all trigonometric functions. If you know the derivative of one trigonometric function, the derivative of its complementary function will be the negative of the complementary function of the derivative. So what am I saying? So for instance, the derivative of sine x is cosine of x. So if you want to do the complementary function to sine x is cosine of x, its derivative will be negative of the complementary of cosine, which is sine x. Same thing with sec x and cosec x. The derivative of sec x is sec x tan x. So the derivative of the complementary of sec x, which is cosec s, will be negative of cosec x cot x. So and so on and so forth. But the one that concerns us here is we want to know the integral of cosec squared x. So since the derivative of cot x is negative cosec squared x, if we would undo that, then it means that the antiderivative of cosec squared x dx is just going to be negative cot x. Beautiful. So we have all the ingredients we need to cook. So I is our integral. So using the IBP, the integration by parts formula, I will be uv. In this case, u is natural log of sine x times negative of cot x, then minus integral of v, which is negative of cot x, times du. So, and you know du is also cot x dx. Beautiful. So this is negative cot x natural log of sine x, then negative of negative is positive, integral of cot squared x dx. So the next thing to think about is the integration of cot squared x dx. Another thing, from the list that we have written here, we can see the integral. We know the integral of cosec squared x, it will be negative tan x. We know the integral of sec squared x, it will be tan x. But there is no cot squared x here. However, since we know the integral of sec squared x and cosec squared x, we should think of a way to relate cot squared x with one of them. And that comes from the Pythagorean identity. You know, the basic one, sine squared x plus cos squared x is equal to 1. If you divide through by sine squared x, you get 1 plus cot squared x is equal to cosec squared x. Beautiful. That tells us that cot squared x is equal to cosec squared x minus 1. So that means we can rewrite this, our integral, as negative cot x ln of sine of x plus the integral of cosec squared x minus 1 with respect to x. Now, this is simple because from what we have on the side here, we know what the integral of cosec squared x is. So this is going to be negative cot x natural log of sine x plus, so the integral of cosec squared x is negative cos x, and the integral of minus 1 is negative x plus c. We are almost there. So this is negative cot x natural log of sine x minus cot x minus x plus c. And since cot x is here and is also here, I can factor that out. So negative cot x, then natural log of sine x plus 1. We are factoring out negative cot x. So minus x plus c. Okay, so that settles the other one. The third one on the list, my favorite of this whole stuff. Copy, paste. So let's call this number 3. In this particular one, you're given a definite integral. The integral of f of x from 4 to 15 is equal to 25, and we are told to find the integral of this. So basically, when you have questions like this, what should come to your mind is U substitution. Okay, so let's call this I. To find I, integral of 3 over 2 to negative 4 of f of 2x plus 12 dx. So first and foremost, that order does not make sense. So I need to change that order. But the property is that when you change A to B to B to A, it must attract a negative sign, f of x dx. So I can deal with that immediately before thinking of something else. So this is from negative 4 to 3 over 2 of f of 2x plus 12 dx. Now the next thing, we cannot break f of 2x plus 12 to f of 2x plus f of 12. That is not possible. We don't know what kind of function f is. But one thing we can do is we know what will happen anytime we have f of any variable. Say t, say u, say r du. So far it goes from 4 to 15. So the question is, can we transform this given integral to look like this? So let's see. So let's make u equal to that expression inside. So let u equals to 2x plus 12. And if u is equals to 2x plus 12, it is going to have an effect on both the x and the limit. So this means that the u is equal to 2 dx, and then that means that the x is equals to the u over 2. Also, when x is equal to, because these limits were given to us in x, so as we are traveling to the u world, we need to change the limits as well to u. So when x is equals to negative 4, u will be 2 times negative 4 plus 12, which is going to be 4, because that is 12 minus 8. And when x is equal to 3 over 2, u will be equals to 2 times 3 over 2 plus 12, which is equals to 15. It's making sense. It's making sense because we have 4 and 15. So I can be transformed into, so instead of negative 4, there's a negative here first. And instead of negative 4, we are going to have 4. And instead of 3 over 2, we're going to have 15. And it is now f of u times the u over 2, because the x has changed into the u over 2. Now what do? We factor out the constant 1 over 2. So negative 1 over 2 integral of from 4 to 15 of f of u du. But that is beautiful. We already know what that is. We're given. That is just 25. So this is equal to negative 1 over 2 times 25, which is equals to negative 25 over 2. You see why it is my favorite. It's very sweet, but it only requires that you know what to do. Unless it is not going to be sweet, it is going to be sour. All right, the next question on the list, let's see. Integral. So when you combine powers of sine and cos like this, there is a very common trick. And what is that trick? Is to make u equal to one of them and collapse the other into the unique one. So what do I mean? So since this one is underneath the square root, I cannot cancel it out. So it is the ripe candidate for u. So let u be equal to cosine of x, just cosine of x. So then we want everything to be in terms of cosine of x, except because from here we can see that the u is equal to negative sine x dx. So if I need just one sine x out of this, so if my integral is integral of 5th root of cos squared x sine cubed x, I can rip out one of the sines. So that will be 5th root of cos squared x sine squared x times sine x dx. So we know this now relates to this. So that will change to the u. We know that this will change to u squared. So we need this one also in terms of u. And that is where the Pythagorean identity comes into play. We know that sine squared x is equal to 1 minus cos squared x. So this means the integral will change to the fifth root of u squared, or let me write it out in this way first. Cos squared x times 1 minus cos squared x times sine x dx. So this is equal to the integral of the fifth root of u squared times 1 minus u squared times negative of the u. So that changes things to u. If we change this to index form, that is 2 over 5 into bracket u squared minus 1 du. You see, I have acted on this bracket by the negative sign, so it has changed the order of subtraction. So, and if we expand this gives us the integral of u raised to power 2 over 5 plus 2. 5 times 2, 10, 10 plus 2, that is 12. So that is 12 over 5 minus u raised to power 2 over 5 du. Now, it looks very simple because this is just a power. And we know the reverse power rule of integration, the x, when n is not equal to negative 1. So x raised to power n plus 1 over n plus 1 plus c. And if n is equal to negative 1, this is just equal to natural log of x. So in this case, since n is not equal to negative 1, we say this is the u raised to power 12 over 5 plus 1 over 12 over 5 plus 1 minus u raised to power 2 over 5 plus 1 over 2 over 5 plus 1 plus c. And that is equal to u raised to power 17 over 5 over 17 over 5, which is 5 over 17 here, minus u to the power of 7 over 5 over 7 over 5, which is 5 over 7 here, plus c. And finally, we remember what we started with, u equals to cos x. We bring back the u. So that will be 5 over 17, then cos x raised to power 17 over 5 minus 5 over 7 cos x raised to power 7 over 5 plus c. Sweet. The next one, which I believe is the last one. Yay, finally we are getting to the end. So copy. Let me see, will this space be enough? So what do we have here? Okay, we have sec theta, we have sine theta, we have cos theta. What should we try here? All right. We know the integral of sec squared theta. All right, let's play some magic here. So let's multiply through by sec x. So this becomes integral from 0 to pi over 4 of sec theta rather. Sec theta times sec theta over sine theta times sec theta plus cos theta times sec theta d theta. Again, like I said, integration and mathematics at large, it helps if you have seen something similar before, and that is why it is good to practice a lot with a lot of questions. If you are seeing a question for the first time in the examination, it is not impossible for you to be able to do it, but it could be very technical Okay, not difficult, not impossible, but it could be, you could waste some precious time trying to look out what to do. So in this case, sec theta times sec theta, that is just sec squared theta. So we have 0 to pi over 4 sec squared theta. And this is exactly the reason why I have decided to multiply by sec theta, because I can see that sine theta times sec theta. Sec theta is 1 over cos theta. So that will just give us tan theta. So that gives me something in the denominator whose derivative is in the numerator, which is good. Very good, especially since cos theta times sec theta is just 1. Very good. Anytime you have a situation where you have the derivative upstairs and you have f of x plus a constant in the denominator, just set u to be that denominator immediately. So in this case, u is equal to tan theta plus 1. And then that means that the u is equal to sec squared theta d theta. Oh, looking good already. And again, like we did in the previous question, we changed the limits of integration. When theta is equal to 0, u is equal to tan 0 plus 1, which is 0 plus 1, that is 1. And when theta is equal to pi over 4, u is equal to tan pi over 4 plus 1. Tan pi over 4 is 1, 1 plus 1 is 2. So our integration will change to that of from instead of 0 to now be 1, and instead of pi over 4 it will be 2 of, we have sec squared theta d theta in the numerator, so that is going to be du then over u, or 1 over u du. And that is one of our favorite integral. In fact, that's what I've written here. Integral of 1 over x is natural log of x plus c. So it means this is natural log of u, and using the fundamental theorem of calculus, this is from 1 to 2. That means this is equals to natural log of 2 minus natural log of 1. But hold up, natural log of 1 is just 0. So this is just natural log of 2. Very beautiful. And with that, we have spent long enough on this video, so I'm going to wrap it up here. And in the next one, when we come back, I'm going to look at some questions, some smooth derivative questions that are on this problem set. But until then, stay warm and enjoy the mathematics flavors that are around us. Bye.